Come on, don't do this to me again. There we go. So this lesson is inverse functions. Okay, inverse functions are important to solve equations where you can't just do algebra to both sides to isolate a variable or factor so that you can set each factor equal to 0. There are functions like that, some that you've already dealt with, which I'll show you on the next slide. So they become important. You've used them, right? You've probably already used them up to now, but you may not have known where they came from. So let's see. Come on, don't. Seems like everything's slowing down here. There we go. So if we have a function f of x, the way you write the inverse of the function is f with a little superscript of -1, right? You might say f to the -1 of x, f inverse. Either one of those would be fine. You know, the place where you might have encountered this before, you probably did, you may not remember it, but you probably did, was when you did this. Right triangle trigonometry, x degrees. Right? If you had a right triangle and you knew two sides, then you were supposed to be able to find one of the acute angles. And if you don't remember all this, that's okay. You'll see the part that's pertinent to what we're doing right now. Usually you go with respect to this angle, these two sides are opposite and adjacent, and then you say, which of my three trig functions, sine, cosine, and tangent, uses opposite and adjacent, and that's tangent. And so you go, you set up an equation. Tangent of x degrees equals 23 over 45. But you've got to solve for the x, and it's inside of a function. You can't divide by the letters tan, right? It does not work that way. What you can do is you can take, based on the things we learned in the lesson today, you could say, I'm going to take tan inverse of both sides, and when you take the tan inverse of the tan, they cancel each other out, and all you get is x. You've solved for x by using the inverse function. And if you look at your calculator, in fact, you have those buttons, right? Above your sine, cosine, and tangent, you have sine to the -1, cosine to the -1, tan to the -1. And this kind of solving, I mean, we do that in geometry. Everybody should have had it in geometry. If you got to the trigonometry at the end of last year, then you might have seen it again there. If you didn't, you definitely got it in the geometry part. So that's inverse functions. That's why we use inverse functions, to solve equations that we don't have another method to solve. For example, like I said, after we do this chapter, we go to the logarithms and exponentials. And the reason you do that right after you do this is because logarithms and exponentials are inverses of each other. So we'll be able to use one to solve the other, right? Just like that. Now, the thing about a function and its inverse, it should be the case always. If a function has an inverse, it should be that, for example, if f of 1 equals 3, then f to the -1 of 3 should equal 1. They should point in opposite directions, right? You can always undo what the function did by taking the inverse of the output. Okay. And one other thing I should say here is that, you know, when I took the tan -1 of the tan, that's composition. I mean, how do you do that? It's the composition. Tan inverse, little open circle, tan. That's what it is. Okay, so inverse functions. Right. Some inverse functions, you could probably just kind of guess what they are. Like this first one, if the f of x is x plus 4, meaning you get all these points, 1, 5, 2, 6, 3, 7, 4, 8. The inverse function, what would be the opposite of adding 4 to everything? Subtracting 4 from everything. So the inverse function is x minus 4. And you notice the effect on the points, right? In the function, you had 1, 5. In the inverse, you got 5, 1. It just switches the x's and the y's. Right? So every point here, if you switch the x and y, you get the inverse. Right? So if you have a function, this function is x plus 4, it has a domain, right? The domain are all the x values that you plug in, and they go through the function to generate y values, right? But the domain, the range of this function becomes the domain of the inverse. Domain and range of the inverse switch with the domain and the range of the function. Okay, so this is the arrow for the f inverse. It's going from this circle to this circle. So now this is the domain of f minus 1. This is the range of f minus 1. Domain of f is the range of the inverse. Range of f is the domain of the inverse. That becomes like the number one probably complicating factor for everything that we do in this lesson. It's just that's probably the one detail that we don't do well with at all. Is you just always got to remember about the domains and ranges switching. It makes a difference to the answers you get a little bit. So just again, notice x's and y's switch, domains and ranges switch. Okay, and so here's the property, the one I showed you on the first page with tan inverse of the tan canceling each other out. As long as a function and its inverse are both functions, mean passing vertical line test, then if you take the composition of a function and its inverse, in either order, it doesn't matter if it's f of f minus 1 or f minus 1 of f. In either case, everything else will cancel, and all you're going to be left with is an x. Right? That's the property that allows us to use the tan inverse button or the sine inverse button, or to take the log of an exponential or the exponential of a log and solve equations that could not be solved otherwise. Good. Okay, Connor. So the first examples here are just kind of like guessing an inverse. If f of x equals 1/5 of x, what do you think would be the inverse of that? Right? This means like if I put in x equals 5, y equals 1, what would be the opposite? What would take you from 1 to 5? Yeah, how about, you could think of it like 5 over 1, or how about just 5x? I mean, if you had to, you could try a couple points, right? What if I do f of 5, right, will be 1/5 times 5, which is 1. So it should be the case that f inverse of 1 equals 5. It should go exactly in the opposite direction. Okay, so plug in here, 5 times 1. And it does. Good, good. Okay, now the first kind of problems we get in the homework are, it says verify the two functions are inverses. So how do we verify? We take the composition of the two functions and we see if everything cancels, and what you get is x. So this is actually dealing with the two functions that we just introduced, that we just guessed, right? So now we can verify. We came up with our our guess, but now we can prove that it's true. So again, how do we do a composition based on the homework last night? The F little circle of F minus 1 we would rewrite as F parentheses F minus 1 of X. Right? Just rewrite it like that, and then how do we proceed? We replace the inner function with what it equals. Okay, the F minus 1 is 5X, so replace it. And then we evaluate the outer function, meaning plug in that 5X in the place of X right there. Right, so that'll be 1/5 times 5X, and the 5's cancel, and all you're left with is X. That's what we mean by everything canceling and all you're left with is an X. There you go, it's just X. Okay, now let's reverse the order and see what we get. F minus 1 of F of X, F minus 1, and we'll replace the F of X with what it equals, 1/5 of X. And then we'll evaluate F to the minus 1 of 1/5 X. Which is going to be like taking that 1/5 X and putting it in the place there. 5 times 1/5 X. And the 5's cancel, and all that's left is X. So that verifies that those two functions are inverses, because we did the composition in both directions, and everything canceled, all we had was X, both times. Okay, this one says, which of these two functions could be the inverse of that function? So again, how are you going to tell? You're going to take the composition of functions and see which one leads to X being the result. Let's say we start with this first one, the F of G of X, right? So we need to do twice. Well, I'm going to do F of G of X first, right? F of G of X would be F of 7X plus 4. Right, I just replaced the G of X with what it equals, and now I've got to do the F of 7X plus 4, which means take this and put it in the place of X there. 7X plus 4 minus 4 divided by 7. Simplify. What simplifying can you do in the numerator? The 4's cancel, right? So as the first step, you get 7X over 7. And then you cancel the 7's. So it looks like that first one could be the inverse. What would I have to do to make sure it's the inverse? We did the F of G, but don't we also have to do G of F? You got to do the composition both ways, and shows in both ways everything cancels and you're left with an X. So now we'll do the G of F of X, which is G of X minus 4 over 7. So this time we're going to try to place all of this in the place of X here. Right, so that'll be 7 times X minus 4 over 7 plus 4. Right, simplify. What's the first simplification here? The 7's cancel, right? The 7, which is multiplying here, and the denominator of 7, they cancel. So now we've got x minus 4 plus 4. And now we cancel the 4's, and we get x. Okay, so is g of x the inverse of f of x? Yeah, we just showed that it is. Now, you could try the second one, right? I'll set it up, but sometimes these can become very not so easy to prove in the counter example in a way. Like if I try to do, let's say I try f of h of x, f of h of x, right? That means I've got to replace the h of x with this, f of 7 over x minus 4, and then I've got to plug in that whole 7 over x minus 4 here. So in the numerator, it's 7 over x minus 4 divided by 7. Now, sometimes if you're looking at that and you think, well, there's no way that's going to cancel and just give me an x at the end, it's actually, maybe it would. You know, maybe if you remembered how to find a common denominator between these two fractions in the numerator, that you'd get some surprising cancellation that would work out. But sometimes you go down that path and it just turns into something like it's really complicated that you're not quite sure if you did something wrong or there's maybe just something else you've got to do. So I can say this one can't be simplified to give us x. And so instead of just going down a stray path that may lead to nowhere, since we already verified the other one worked both, that's probably better. If I would have started with this and I got that and I wasn't very confident in what I had, I probably would have said, let me do the other one, see if the other one works out a little better before I get too lost trying to do this. So this is not equal to x. So the inverse was g of x. Okay, now if you take two functions that are inverses of each other, right? Here's the f of x equals 2x minus 3. And the inverse, you could take my word for it for now, is 1/2 of x plus 3. Okay, and you graph the two lines, right? Here's the function, and here's the inverse. I mean, notice all the points that they've plotted on here, right? On the function, we've got the point 2, 1. So on the inverse, we should have the point 1, 2, right? On the function, we've got 1, negative 1. So on the inverse, we should have negative 1, 1. You should just switch the x's and the y's, right? At 0, negative 3, negative 3, 0, negative 1, negative 5, negative 5, negative 1. And notice, right, that the point 3, 3 was also on the function. But what do you get when you switch those two? The same point, right? So it must be the case that if you've got a point which has got the same x and y coordinates, it's got to be on both of them, right? So what it turns out is that if you have a graph like that, a function and its inverse, it should look like that they are symmetric with respect to the line. I think I did this last time. Watch this. I can go. They should be symmetric with respect to that line. You know, the function on this side, the inverse on this side, it should look like they're mirror images of each other. So this is a line of symmetry. Okay. Right? So the graph of a function and its inverse are symmetric with respect to the line y equals x. Right? That is a major understanding here. It should look like the function and the inverse are just flips across the line y equals x. There's y equals x. Right? We dealt with y equals x when we did the common functions or parent functions. That was the identity function. The identity function is x's and y's are always equal. I mean, I would expect, well, We're not going to have a separate test. We're just going to have a 9-week test. But that's the kind of question, what do you expect of the graph of a function and its inverse? They are symmetric with respect to the line y equals x. We're good? Okay, now not every function has an inverse. And an example of that would be f of x equals x squared. Right? We know what that graph looks like, right? That is a parabola with the vertex at the origin. And this is the table of values that would make up the graph of y equals x squared, right? At -2, x equals -2, y is 4. X equals -1, y is 1. X equals 0, y is 0. So there's our table of values. Now remember, the inverse function, which is this, should have all of these coordinates just flipped. So instead of -2, 4, you got 4, -2, right? So if I take all these values and flip them, that's what this table of values is right here. Now notice, if I had to ask, is this a function? Well, what would we be looking for to tell us whether it's a function in a table of values? Repeated x values, right? And you do have repeated x values, right? You have at x equals 4, y is -2. But at x equals 4, y is also 2. 2 values. What's that? And the ones, right? So we would expect, like we said on the very first slide, that if f of, let's say, 2 is 4, then it must be the case that f of 4, f to the -1 of 4 equals 2. And it's not, right? Because all f to the -1 of 4 is also -2. That's why it doesn't have an inverse. They got to point exactly to each other, not sometimes, but all the time. So that's an example of a function that does not have an inverse. Okay, so now I think this is a writing side. Okay, a function that has an inverse must have only one y value for each x value. Okay, that's what we mean by a function. But then it also has to have only one x value for each y value, so that when you switch them, you've still got a function, right? When that is the case, that's called one-to-one. A function that only has one x for each y and one y for each x is called one-to-one. Right, so we're going to learn how to find an inverse, right? Algebraically, how do you find an inverse? But we wouldn't find one unless we can first say for sure that it has one. There's no point trying to find an inverse that doesn't exist. So we need to check before we start if our function is one-to-one. If it is, then we proceed. And luckily, there's a very easy test for this. Very easy test. Okay, a function is one-to-one, meaning it has an inverse, if it passes a horizontal line test. Remember, it already passes a vertical line test because it's a function. But if it has an inverse, it also passes a horizontal line test, meaning that you could pass a horizontal line and it'll only cross the graph in one place. Right? This is x squared minus 1, so it's a parabola. Right? That's a function, passes a vertical line test, but it does not pass a horizontal line test, so it does not have an inverse, not 1-to-1. Right? Right? But this one looks like it's 1-to-1. Right? Because I can't imagine anywhere on that graph where I could cross in two places. I mean, I use my imagination. It looks like it's just one, so this is 1-to-1. And to put it in other terms that mean something to us at this point also, you can say that a function has an inverse if it's either always increasing over its entire domain or always decreasing over its entire domain. Then it's 1-to-1. You know, something like this does not have an inverse because it's actually decreasing and then it's increasing. Okay, so that doesn't work. We used to have 3 checks for this, and the newer textbooks are just doing the horizontal line test. Good. Okay. Okay, so how are you going to determine whether something has an inverse? You're going to graph it in the calculator, and you're going to see whether it passes horizontal line test. Or if you need to pass it, put it in a calculator. You know, the first one, sometimes you should be able to recognize by the kind of function that it is whether or not it passes. But if you can't, and there'll be some of these functions that you probably don't recognize just by looking at it what it is, then by all means put it in the calculator and check. Right? This first one, y equals 1/2 x, right? 0.5 parenthesis 3 minus x. Graph. Does it look like it passed the horizontal line test? Yeah, so it's 1-to-1, has an inverse. Now, what kind of a function is that? Based on the power of x, what kind of function is it? It's linear, right? And linear functions, in every case except for one, will always have an inverse. What's the one exception to the rule? What's the one straight line that wouldn't pass a horizontal line test? A horizontal line, right? So if you had like y equals 4, that's a horizontal line, that won't have an inverse. But every other linear function will. So when you see something like that, you see that it's linear and it's not just y equals a constant, it has an inverse automatically. Okay. How about do I need to put this one in the calculator to know what the graph looks like? What's the absolute value look like? It's a v, right? So just imagine, without graphing it, without putting it in the calculator, just picture that v. Does it pass a horizontal line test? No. So it doesn't have. So you don't even need to put it in the calculator if you already kind of in your mind can picture the shape, right? So this is a yes, and this is a no. Okay. Okay, so once we know that a function has an inverse, then we've got some pretty finite steps here to actually find the inverse. And you should have seen these last year. And if you want to copy them down, you copy them down, and then we'll use them on the next slide. Notice in the step 2, right? You switch the x and the y's, right? Just like we said on the very first slide or two, switching the coordinates of the x and y. Okay, that's what you're doing right there. Switching the domains and ranges, switching the x's and y's. Let's see about this. We are on page. It's too complicated. Okay, I think before I do that one, I'm going to do an easier one. Okay, let's say we wanted to do f of x equals, I'm just making it up, 2x plus 1, a linear function. So in terms of, does it have an inverse? You could say right away, yeah, it has a function because it's linear and it's not a horizontal line, so it does have one. So just to follow the steps, I would replace the f of x with a y, right? I would switch the x and the y with each other so that it looks like x equals 2y plus 1. And now, because the y is in the middle of the expression on the right, you've got to solve for it, right? It's no longer isolated. So you've got to solve. Subtract 1. Divide by 2. And then the last step, replace the y with f inverse of x. Right, those are those basic steps. Now, when you have a straight line, again, a straight line that is not horizontal, it's not vertical, it's got some tilt to it, what are the domain and ranges for all straight lines that are not horizontal or vertical? It's all real numbers, right? These lines go on forever, up and down, left and right, all real numbers, all real numbers. So when we switch the x's and the y's, we still got domain of all real numbers, no issues with domain and range, none, 0, right? The only place that this gets a little more tricky is on something like the next one, which is why I didn't want to have that be the only one you saw. I mean, that's a clean one. Some of the problems you got in the homework are just as clean as that, right? It's a little more tricky when you do something like the square root of something. Okay, and let's see why it's a little more tricky. So here's our steps. First step, I should replace the f of x with a y. Okay, that's the easy part. And then swap them out, right? X for y, y for x. Looks like x equals 2y. The square root of 2y minus 3. Okay, now in the solving part, the y is in the middle of the expression on the right. It's actually inside a square root, and the square root is isolated, right? So how do we undo the square root? Square both sides, right? So this is going to be x squared equals 2y minus 3. Okay, now I can get at the y. I can isolate the y by adding 3, dividing by 2. So this will be, go up here, 2y equals x squared plus 3. Y equals x squared plus 3 over 2. I'm going to do it like this. Okay, then I can replace the y with the f minus 1 of x. Okay, we started with a radical function, right? We ended up with a quadratic. Okay, we've been through this already. We went through this with x squared. And what did we say about x squared? Didn't have an inverse. So how could this quadratic be an inverse if it can't have an inverse? And the reason is because, again, you got to take into account the domain and range of the original function, right? The square root function, right, only has positive output. So we would expect that the range of this thing, the range of this one right here, has to be y is greater than or equal to 0. And the domain of it, again, it's a square root. So I would have to take this 2x minus 3, set it greater than or equal to 0, and solve. Right, that'll end up being x is greater than or equal to 3/2. So I need to, because these were the domain and range of the original function, the inverse has to have the flip of those, right? This thing has to have a domain of x greater than or equal to 0. Whatever the range of that is, that's the domain of this. And whatever the range of, whatever the domain of the original function, then the inverse has to have that. So it'll be y greater than or equal to 3/2. Okay, now if I look at the graphs of these things, see if I can squeeze it down here. Too far. If I look at the graphs of these things, oh, darn it, did that again. I want a little more space. Holy mackerel. That is just unacceptable. I'll just do it here. Right? This graph was a radical function and had been shifted to the right 3/2. So it looked like this. 1, 2, 3, 4. So it started right there on the x-axis, and like radical functions do, or square root functions, it went up like that. Right? This function is a quadratic. It's a parabola. Its y-intercept is 3/2, so it goes up here, right? It's a parabola that goes up like that, and it goes up like that. But because the domain is x greater than or equal to 0, that means we only want the part of this to the right of the middle. We don't want x values less than or equal to 0. The domain is going to give us just the right half of the parabola. So I can erase this piece here. And that's because of the domain. And then one last thing I could do, it ought to look like those two graphs are reflected across the line y equals x. So if I just draw in the line y equals x, I would say that looks pretty good. It looks like this is a flip of that across the line y equals x, which it should. If you had the whole parabola there, it would not look like that. But if you just restrict it to the x greater than or equal to 0, it does. Okay. So let's see. So now we know what inverses are. Okay. We know how we can tell whether a function has an inverse, horizontal line test. You really need to know that that's called one-to-one. The 9-week test, which has a lot of it is just coming from things from downtown. I believe they use the terms one-to-one in there a few times. So you got to know what the one-to-one means. Okay. And then you should know how to find the inverse, right? Switch the x and the y, solve for y, that kind of thing, if it has an inverse. All right, in the homework problems here, I believe these first three are verify an inverse, right? So take the composition, see if everything cancels, and you just get an x. I think these next four are graphs. They're right in front of you. You don't have to put them in the calculator. You just have to look at them and say, do they pass horizontal line test? That's it. The last bunch of problems, 57 to 64, if you look in your book, what page is that again? 108. 108. Okay. Let's see if I can go forward or whether it's going to tell me I got to. And like usual, it probably logged this out. Prerequisites. We go down to the end. And we go up to 108. And I think it's 109 actually. That's these problems here, right? So it says, determine whether the function has an inverse. And then if it does, find the inverse. So first, put it in the calculator, see whether it passes a horizontal line test. It says that 57 to 64 all, that's 7 problems, but about half of them aren't going to have inverses. You're not going to end up doing anything. You just got to recognize which ones they are. And notice on, for example, this one here, I mean, that's a parabola. And you would think that a parabola would not have an inverse, right? But it's got a domain statement after that. It's saying only use the part of the parabola where x is greater than or equal to -3. So let's see if I can do this. I mean, we know that that parabola would be shifted 3 to the left because that's what a +3 inside would do to you, right? And it would look like this. But they said only x greater than or equal to -3. So we're really only taking that side of the parabola. So that will be 1-to-1, just so you know. Okay, that because of that domain statement, it will have an inverse. And I think that's the only thing. The rest of them, you can tell, like, you can tell linear, I mean, it's got an inverse. I'll leave it at that. But you should make sure you check before you do anything, because a fair number of these don't have inverse. Okay. And I got to stop.